This is if else day 3, and we have this program, and if we run it, all it's going to do is right now is ask for a number, and then it puts that number into the variable num. So let's say we put in 11, not going to do anything. The first thing we have is switch case, and this replaces having lots and lots of ifs, and we can do it very simply by doing a case. All right, so we got switch, and this is going to read the number. So this is going to use the number that we put in num. So it's going to use num. Now, if I type in 11, it's going to do this line right here. Now, we could have multiple lines. We could have not just one line printing it, but we could have anything we want it to do. If we type in the number 11, it's going to do this block of code. It'll keep doing blocks of code until it sees the word break, and then it stops the switch case. So if we run it, enter in 11, it's going to say num is 11. If we run it again and we say number 22, it reads 22 into the variable. It looks for 22, and if it's 22, it does num is equal to 22, like that. Now, if we have a default case down here, and let's say we don't have let's try the default case first. In other words, nothing that is listed in here, like 55. So we do 55, and it says does not equal. That's what we told it to. Well, if we don't have that in there, I'm going to comment this out, and we run it, and we put 55. It just doesn't do anything. So this one covers all cases right here if you have default. Switch case executes all. Let me pull this down here. Switch case executes all lines until a break is reached. So we can enter a number again. So I'll enter the first little piece, and then we go, let's enter 11 again, and notice it does all three of these lines. This one, and this one, and it'll keep going until it reaches the break. That'll tell it to stop. So now if we do enter number 11, enter 22, it does these two lines. It does this one and the next one, and then it hits the break. Oh, how far should we drag this? Let's go all the way down to right here. In order of operations, AND evaluates before OR. So if we have integers x equals 5, y is 8, z is 10, if x is equal to 5, or y is equal to 3, and z is equal to 7, this is done first. Then it'll evaluate x equals 5 compared to what it just evaluated with the OR. Now, if we want the OR to be done first, all we got to do is put this in parentheses. Now the OR will be done first, and then the AND will be evaluated. So if we go 11, 11, and then this will be true, and this one will be false. Now short circuiting. Let's talk about short circuiting. Let's pull it down. I'm going to pull this down to line 46. Short circuit. As soon as the compiler knows the outcome, the evaluations stop. In this case right here, z does not need to be incremented because x equals 5 is already true. So we have 5, 8, and 10. This says if x is equal to 5. Well, that already evaluated to true. So here I've said if this side is evaluated, add 1 to z. Z would become 11. 11 does equal 11, and this side would also be true, but it never gets to this. Once one side of the OR is true, it doesn't have to evaluate the other side. Now notice when we run this, z is still at 10 because this never happens. It short circuits. So z down here at the bottom will be 10. This never happens. It doesn't have to happen because one side of the OR is already true. Doesn't have to evaluate the other side. Doesn't have to find out if it's true or false. What do we have here? 5, 8, and 10. An AND. X is equal to 5. That is true. But an AND, both sides have to be true. So this time z actually does become 11. Now this evaluates to true. Now it has to check the other side to see if that's true because with an AND, both sides have to be true. So when we run this one, z will actually become 11 on the very last line. So now z down here becomes 11. This will not short circuit. It can't short circuit when it's checking both sides of AND, unless one side is false. And I think that's the next example that I have here. 5, 8, and 10. If x is equal to 6, that's false. Now, if one side of an end is false, that means that it's already, the whole thing's false. It doesn't have to go to the other side and evaluate. So Z never becomes 11 here because it doesn't evaluate that side. This is false. Doesn't matter what the other side is. It's false. So it short circuits. So when we run this, Z will remain 10 at the very bottom of our output. Z stays at 10 on this one because this short circuited. A single OR and single AND do not short circuit. So none of this will not. If X is equal to 6, that'll be false. Plus plus equals 11, that's true. So this side will be evaluated because we used the single and ampersand, or however you say it. So down at the bottom, Z actually becomes 11 down here because with the single one, it will not short circuit. And we rarely use the single one. We almost always use the double one for efficiency of the program. If it doesn't have to be evaluated, why would we use the memory? Why would we use the computing power to evaluate if we didn't have to? The last thing for today is DeMorgan's law. Here's what DeMorgan's law says. Not A and B is the same as not A or not B. And I describe it kind of as the distributive property, except you have to change the N to an or the or to an end. So if it's not A and B, that's the same as doing not A or not B. So now if it starts with or, you just have to switch it to and. So not A or B is the same as not A and not B. So both become not, and you have to change the N to an or the or to an end. Now let's finish this little program here. I wrote a note to myself, change A and B values. So this system out print line, false and false. This will be false, but the not will be true. Now, if we do not false, that's true. So the or is already true. So both of these should be true. They'll always be the same value because that's what DeMorgan's law says, that they're the exact same thing. So both are true. What if I change this to true? The point is the last two lines down here will always be the same according to DeMorgan's law. Doing not A and B is the same as not A or not B. So when we run this, they're both true. What if we make this one true? When we run this, 11, 10, they're both false. They'll always evaluate to the same thing, and that's what DeMorgan's law is all about. And we'll talk about this a little bit more throughout this unit.